Yeah, so welcome to the 12th and final week of the course on scientific computing using Python. So before we begin, any question from the previous week? Anyone? If not, then let's proceed. And one instruction, Professor Verma will take a live session on Sunday, the coming Sunday at 5 p.m. Okay, you will get the link and everything on the portal itself. So that's one important thing. If you want to ask him anything about the course or about the exam, you can do that. All right. So let's begin this week's content. So this was a mix of two things: linear algebra, and the other was Monte Carlo methods, right? Probability distribution and its application. So why do we use linear algebra in first place? Well, to start with, there is nothing in the world which is linear, right? Nothing is truly linear. You might say that this is linear, but that spring mass system is linear. All of them is kind of approximation. For example, quantum mechanics. Well, that is Schrodinger equation is linear. Then you take into consideration open systems and stuff, interactions, and even it can get nonlinear. All right, but the fact remains that if the system is approximated to be linear, it can be solved very easily compared to nonlinear equations, and that's why whenever we can make the systems linear, we do that, and then we try to solve it, right? And one of the things we do is play with matrices because they come in very handy in QM and stuff. So what can we do with matrices? First is solving equations, linear equations of the form Ax is equal to b. Right? We have seen some of this in the previous sessions how to do that. So the one method is Gaussian elimination, and we already covered this last time, so I won't go into detail again. But the basic idea is that you have got a matrix with all entries potentially being filled, and that is multiplied by a vector x, which we have to find. This is an and this is equal to some known vector b, right? So this is ax into b, a into x is equal to b. And to solve that, what we do is first make the first entries of each row except the first one 0. Okay, how do we do that? So multiply the second row and use some linear combination of first and second row to get this first element to be 0. Then use these two to make this one 0, etc. Okay, so you got to this part, and that means this b will also be modified accordingly, right? This will be some b, and then it's an iterative process. It's a recursion basically. Do the same thing with this remaining matrix. So you had this one, and now these entries need to be 0. So do some operations and get them to be 0, and so on and so forth until you get a matrix which is upper triangle, which means you can have diagonal which are non-zero, and you can have up entries above this diagonal to be non-zero, but all the entries below the diagonal are 0. Okay, so this is an upper triangle matrix, and this is multiplied with some x's is equal to some b prime prime, right? And then it's very easy to solve because you know that this is just the last variable xn, and that is equal to this last variable of b prime 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 whatever it is. And then using that, we know that this is this combination of last two variables, and we already know the last variable, so we can find this one. Okay, and then you keep on doing the same. So this is one way in which you can solve such equations, and we are going to do one example because it's in the assignment. Okay, another thing you can do is the so-called LU decomposition. And what is the theorem? Theorem is that any matrix can be broken down or decomposed into product of three matrices P, L, and U. P is for permutation, yeah? And it looks like something like this. It's 0, 0, 0, and one entry is 1, and this will be somewhere else, so on and so forth. But in every column, you have just one entry, one and only one entry, which is 1. All others are 0. Same with each row. Okay, so that's the permutation matrix. And what does it do? Let's say I have a matrix, looks like this: 0, 1, 0, 0, 0, 1, 1, 0, 0, and that is multiplied with some matrix. What it will do is it will exchange the rows of this. So maybe second one comes to the first one, third one goes to second one, etc. So rows will be exchanged. Okay, and L is lower triangular. Okay, and U is upper triangle. So in lower triangular, diagonals are always one, and then you have stuff below the diagonals. In upper triangle, diagonals are anything, and you have stuff above the diagonals. Okay, and once you can decompose into this, it's really easy to find A inverse. Okay. And so once you have A inverse, you can do all sorts of things, right? For example, if you want to solve Ax is equal to B, the solution is A inverse B. It's just one step solution. It's just that finding A inverse itself is very difficult. So this is one way in which we can do it. Okay. And then there was a portion on eigenvectors and eigenvalues, which we also did last time. And probably you know how to calculate it and etc. Maybe some of you don't know what is the intuition behind the eigenvectors, and it's as follows. Suppose we have a matrix, okay, A, B, C, D, and we encounter matrix in physics everywhere, right? So it's a good idea to get feel of this matrix. What does it mean? What does it? How do you imagine it? So the way I imagine it is that if I apply this on 1 0, this is 2 cross 2. So what do I get? First entry is A, second entry is B. Okay, so it's this. And if I apply the same matrix on y cap 0 comma 1, what do I get? I get C and D, which means the matrix itself, if I call this matrix M, is first column is where x cap goes, second is where y cap goes. If it is 3 by 3, then this is where third column would be where z cap is, right? So, and one thing to remember is that m times x keeps parallel lines parallel and origin at origin. Okay. So earlier, if our coordinates are like this, you know, the space is like this. What m does is it twists and bands the matrix in such a way that these lines still stay parallel. Okay, and this one is something like this. But origin is where it is, right? Because m times 0 0 will give you 0. Okay. So for example, let's take one example 2 1 and 1 2. So how to imagine this? Imagine this is 0, this is 2, this is 1, 1 2, this is x, this is y. So 2 1 is where x cap goes. Okay. So this, that means a different color, goes to 2 comma 1. So here. So this becomes your new x axis, and 1 2 is where y cap goes. So 1 2 is this one. Okay. So this goes to here. Okay. And in between you have the parallel lines, right? Because so these are all lines which were in original case parallel to x axis. Now they are parallel to this vector. Similarly, these are your new y axis, or the lines parallel to y axis. Now, where would be the eigenvector? Where eigenvector has to be between these two, right? And so it's in fact in this case exactly at 45-degree line, because if you are at here, you have equal component in both the directions, and since these 2 1 and 1 2 are symmetric about that 45-degree line, it will just stay on that same axis, right? This 45-degree line, but it can change its magnitude. So let's take this vector, which is 1 comma 1. Where will it go? So 2 1 1 2 applied on 1 1. So 2 times 1 plus 1 times 1, that is 3, and this will also give 3. So it is in the same direction 1 comma 1, but the magnitude is multiplied by 3. So this is your eigenvalue, okay, and this is your eigenvector. So the eigenvector is that vector which just gets stretched or shrunk, but never gets rotated in any direction. Okay, and where would be the other eigenvector? That would be the perpendicular one, right? So it will be minus 1 2 1, minus 1 comma 1, and you can check what its eigenvalue is. All right, so that's the idea behind eigenvectors, and we have a very nice library function inside the empty library called linear, right? And that can give you all kinds of eigenvalues, eigenvectors, etc. Okay. Any questions so far? And let's talk quickly about Monte Carlo. Monte Carlo is a class of algorithms uh, which work on the principle of probability. To be precise, it's called law of large numbers. It's something that is very so intuitive to us that we don't even bother to think about it much. And what's the idea? Well, the idea is something like this. Let's say you are tossing the coin 10 times, then and it's a unbiased coin. All right. So how many times do you expect it to be heads? 5 times heads and 5 times tails, right? But suppose if you actually do the experiment and if you find out it is 8 times head plus 2 times tails, you will be maybe a little bit surprised, but you won't find it too weird or you won't doubt the unbiasedness of the coin, right? Because this can too happen. But if you do the same experiment, say how many is this? 1 lakh times, then you will say, well, 50k, 50,000 should be heads and 50,000 should be tails, and that is what you roughly, right? You will almost never get 80,000 heads and 20,000 tails. What do I mean by that? The probability of this, which you can calculate, right, is very very small. Okay, so as you increase this n, things happen as you can imagine how they should, right? So the probability makes more and more sense as you increase the numbers. That's a law of large numbers. And again, there is a weak statement, strong statement. If you are interested, you can take a look at it. And in fact, if you look at the average, it goes to the true mean of the your random variable. And if you calculate the distribution itself is a Gaussian. All right. And the width of that Gaussian or the standard deviation decreases as function of n. So that's the idea. So there are two kinds of random variables which are very useful. So random variables. One is uniform. So if you have a random variable x that is uniform between say a to b, what it means is that probability of x1 is same as probability of x2 as long as x1 and x2 belong to a, right? So you have equal probability of any number between a and b. So what would pdf look like? Probability distribution function. So it is 0 up to a and then some constant value and then b. And this constant will be 1 over b minus a. All right. By the way, one very silly question, but if you have not thought about it, what if b is less, no, b minus a is less than 1, say zero point 0.5? Then you have p of x is equal to 1 divided by zero point 0.5, which is 2 if x belongs to a, right? So does this mean that probability of finding x is 2? That is obviously not true, right? So what's the resolution of that? Anyone? Okay. Well, it's a very basic concept. The thing is, p is not the probability of finding x, right? There are infinitely many x. So if you calculate the probability of finding precisely that point, it's always 0. What this is probability distribution function, which means that probability of finding some number that is between x and x plus dx, that is given by px dx. So in this case, it is 2 times dx when dx is very small as it approaches 0. This is the probability of finding something between x and x plus dx, and that is 2 times dx. And because dx is very very small, this quantity is much less than 1. In fact, it goes to 0 as dx goes to 0. All right. So it's important to remember that this is the probability density function. Another distribution that we use often is Gaussian. Why? Because as we saw earlier, the one is central limit theorem. When you have lots of random variables added, you get a distribution that looks like a normal distribution or Gaussian. Same. Okay. So in 1D, it looks like this: 1 by square root of 2 pi sigma square e to the power minus x minus mu square by 2 sigma square. Okay. This is when mean is mu and standard deviation is sigma. Okay. So if you change mu and sigma, your mean and standard deviation change, but this still stays a Gaussian distribution. Okay, which means the integral will always be. Right. And how does it look like? It looks like it has a peak at mu. We have seen this multiple times during the course, right? So there is a peak at x is equal to mu, and the characteristic spread that it has, that is order of sigma. Okay. This is like 2 sigma. Okay. Anything else? Yeah. One remark: if you have some generic random variable, say z, which follows some distribution tz, then how do you generate it? So there is one trick. First, you define its cumulative distribution, CDF. Let's call it C of z, which is just integral from minus infinity to z, E z prime dz prime. So it's the probability that this variable will be less than z. Okay, and then generate uniform x. So x from uniform distribution from 0 to 1. Okay, and then calculate z using C inverse of z. So basically, you have z, so C of z as a function of z, And it starts from 0 and goes to 1, right? This is the only thing that can happen because it's a cumulative distribution. So this is same as saying probability z is less than z, z prime is less than z. So you generate a uniform distribution along this and calculate one x and then calculate the corresponding z. So z such that c of z is equal to x, which is same as saying z is equal to c inverse of x. Oh, sorry, this should be x. Alright. So if you find yourself to be, if you want to find, let's say, a weird distribution, generate a weird distribution, then generate uniform distribution and use this rule to find the new numbers, and these new numbers will follow a distribution, that weird distribution that you were asked. Alright. And yeah, since we are doing Python, we have np.random, and if you do .rnd, you get uniform between 0 and 1. If you go rand n, that gives you normal, which means 0 mean and 1 standard deviation. And these are endpoints. Okay, so here 0 and 1 mean different things. Okay, and you can also do uniform from x1 to a to b, basically. So np.random.uniform a to b, that will generate uniform numbers from a to b. Okay, so why do we do that? You can do multiple things. One is find area, eh, or in other words integral. So first example is calculating pi. For example, calculating pi, I should say estimate. So you create a circle of some radius, say a unit circle. The radius is 1, and then create a box around it, a square box. Okay. So area of circle is pi into 1 square. So just pi. So this radius is 1. Area of square is, it's L into L. So this length is 2. So it will be 4. So if I randomly, let's say this is a target and randomly hit points everywhere inside the circle. Okay. And when I say randomly, I mean uniformly randomly, right? Then what's the probability P that the point will be inside the circle? Well, it will be the ratio of these two quantities, right? So it has to be area of circle divided by area of square. So pi by 4, which means pi is equal to 4 times p. So we can generate lots of points uniformly distributed inside the square and calculate the number of points those are inside the circle, and then find this probability, and 4 times p will be 5. We can in fact do this today. Okay. And in general, you can calculate integrals. If you want to find a to b fx dx, so you have a function a to b. So just create a box around it. Say its length is L. So this length is L. Then we know that we want the area of this. It's same concept as the circle, right? So integral. So we can calculate the probability. Probability is going to be the area inside under this curve divided by the total area, which is L into b minus a. So which means we can calculate I is this probability times the total area, which is L into b minus a. Okay. Few things that we should be conscious of. One is that function could be like this, right? And your a and b could be like this. So you should not select this box. You have to select this box. Other thing that can happen is that function can be negative. So if you are doing something like this, then you have to remember that this is negative area. So when you are calculating the probability, you are using some counts, right? So you have to, here you have to do count minus is equal to 1, something like that. All right. So these are the nuances that you might or might not encounter. And then other thing that we learned about is regression. By the way, if you don't understand something, just interrupt and ask. Okay? And this is different from what we did in the very first class, I guess, or in the first couple of classes, which was interpolation, right? In interpolation, it was required by definition that our function pass through all the points. Okay. But in regression, we kind of admit that our experiment is going to have some noise. So it did not pass through all the points, which is anyway very difficult and in fact impossible if you have lots of points with lots of error. So what we want is best fit curve. It could be line, could not be line. Okay. So that's the idea of regression. And the most general way is to minimize the error using this thing. So this is your estimated function minus the data function. So the data points that are given from 1 to n and square. All right. For example, if you are doing linear regression, then your error will be, this estimated will be mx plus c, right? Or was it ax plus b? Yeah, it was ax plus b. So it will be axi plus b minus the data points, let's say yi. Okay, then square from I is equal to 1 to n, and then we minimize this, right? So minimizing e means we have two free parameters in our model, right? A and b, and we want to find the parameters a star and b star such that this error is minimized, which means the derivative at a is equal to a star will be 0, and also at b it will be 0. And we can explicitly do that. Do we need to do that? I don't think it's required. If you want me to do it, just let me know. But the answer is that a star is average of y x minus b star of average of x divided by average square. And so this is in terms of b star, but b star can be written down as this xy minus xy. So this means average, huh? Divided by x square minus average x square. This is the variance. All right. And probably you have seen this. What you may not know, which I also did not know few days before, is that if x, so this is something that we do when y has errors, right? So it is spread around something, and you can calculate the error or standard deviation in sigma a, sigma b also, right? It's done in the class. But if x, which is the independent variable, so if x is have errors too, what does it mean? It means that you have errors across the y-axis, but you also have errors in the x direction, maybe due to measurement or anything. Then this least square method systematically systematically underestimates the slope, and then there are better methods, better quantities measures to minimize that will give you the better answer. Okay, so if you are doing experiments, then just be aware of this. And so then we looked at some physical systems to make use of this method of, what are these called, this probabilistic methods. So the first method is for Ising model. Yeah, it's called metropolis algorithm. If you have done StatMat, you know that it's a model defined on a set of spins. It could be 1D or 2D or even 3D. So you have spins on a grid, right? So this is I is equal to 1, 2, 3, 4, etc. And j is equal to 1, 2, 3, 4. So for every point ij, you have a spin that is plus 1 or minus 1, right? Up or down. And then you calculate energy of this entire grid, the entire system, as sum over Si times Sj with some coupling, that is J, and negative sign, because if Si and Sa are of the same sign, then it will be positive, and that is energetically favorable, right? So this J is positive coupling constant, and the energy is negative. And so I should not write Si. Ij are indexes for the x and y. Maybe I can say Sk and Sk prime, such that K, K prime are neighbors. Okay. So for example, this is your K, this is your K prime, then this product will be minus 1. Okay. So you do that for each neighboring pair, and then take sums. And if they are randomly plus and minus, then sometimes the product will be plus 1 half the times, and half the times the product will be minus 1. So this will be roughly 0 for random or isotropic phase, and this will be non-zero close to some highest quantity for aligned spins, right? And the rule that this system follows, in fact all the system, is this one, that probability that some state alpha of this grid occurs is proportional to e to the power minus beta times that energy of the grid. Okay, so where beta is 1 over kBt. So we are assuming that we have some temperature T and the system is at thermal equilibrium at that temperature, which means we can write P of alpha, normalize it by this factor, right? Sum over all such states. Okay, so and now we want to generate this distribution, but the only difficulty is that there are so many states. So for n cross n, we have n square sides, and every side can be plus or minus, which means we have 2 to the power n square states, which is just simply not possible. So we want to generate a subset that follows this distribution, because if we can do that, then we can calculate the properties of this system as function of temperature, etc. Right? And for doing that, we have the Metropolis algorithm. Right? And so you start with some state alpha, and then generate beta, new state, by randomly flipping one set. And if E of alpha is less greater than E of beta, so you are decreasing energy, which is good, then accept B, accept beta as the new state, right? As new state with probability 1. So just accept it. And else, which means if E alpha is less than E beta, so that is not favorable, right? Then accept beta, but with only some probability, with probability, and that probability is e to the power minus E beta minus E alpha divided by dt. Okay. And if you do that, then you will generate a sequence of states, and all. Then if you calculate the distribution, it will follow this Boltzmann distribution. Okay. So that is the idea, and this is a classical algorithm. Right? Similarly, way you can in fact design neural networks. So those are called Boltzmann machines. Okay, and you can make it recurrent also. So recurrent Boltzmann machines, which kind of learn the patterns in the states, and then they can generate the states which follow this distribution. And in fact, the person who made this won Nobel Prize this year in physics. So Nobel Physics 2024. So you see how ideas percolate from one field to the other. Okay, and the other example that we saw was self-organized criticality (SOC), the famous Burbach. He also has a book with I think the same name, which I'm trying to read right now. And he made this 10 file model. The book is very nice if you are really interested in this kind of stuff. And I won't go through the details, but the basic idea was that you have a grid, and every grid point has some number of cents, right? And once you make that grid, put 1 cent somewhere, and if that causes an avalanche, which means the number crosses some threshold, then each cent goes to the neighboring cent. Okay, and that might cause an avalanche here. Okay, so you record the number of avalanche. Okay, or rather the size of avalanche. So in this case, let's say after 2 avalanches it stops, so S is 2. So you keep on doing that, and then record the different sizes and how many times it occurs. And what you observe is that it follows a power law. So the histogram of S will follow some power law. So if you plot it in log scale, log n of S and log of S, then you get an almost a straight line. Okay, and there is a very deep and rather interesting physics behind why this happens. This also happens in our brain apparently. And it looks like a very general phenomena and very interesting. Okay, so I think this was it. And yeah, in the concluding lecture, he remarked on few things. One was ML AI, right? So he gave examples of I don't remember some neural networks, etc. But now we know that it has advanced even more. We have large language models, right? ChatGPT, Copilot, everything. We have recently AlphaProof, which is by Google. Okay, and in it generates proofs of math questions, and it is at par with silver medalist international mathematical Olympiad. Okay, so it has become much more smarter than us. Maybe ChatGPT is not so smart if you give them some math problems like solving eigenvalues, eigenvectors. Sometimes it does mistakes, but this guy is simply too brilliant. Okay, and again, Google also had AlphaFold, which solved the protein folding problem, which also got Nobel Prize this year. Yeah, Nobel in Chemistry 2024, along with another guy, David Baker, who also worked on ML to find protein structures. Okay, so ML is definitely one thing where computation is going. And while we are all praising computation and everything, we also know that theoretically, not all is computable. So his professor gave the example. It's called halting problem, which is very famous non-computable problem, and it's related to Gödel's theorem and stuff. So this is where the limitation of computer is. Okay, and it's a theoretical limit. So it's not like we are not able to make a fast processor or very smart AI. Does not matter how smart, how fast, how big your computer is. There are several problems that will never be solved by a computer. Okay, so if you are interested in this, just take a look at cutting problem and Gödel's theorem. Okay, so with that, any questions?
Actually, on that initial distributions, no, one of the question was there in assignment.
Mhm.
Some of my marks were different answer, and I got different answer. So I was that Gaussian distribution only. Some
Yeah,
this x minus mu square when we do, whether we should consider the constant term that we are getting in calculation or not was my doubt.
yeah. We'll see. We are going to do exactly the same question. In fact, that is the first question. Are you talking about this question?
Yeah, yeah, yes, yes,
Yeah.
yes.
So let's do this question and then tell me if it answers your query.
Yeah.
Okay. Okay. So the question that is given is you have p of x, which is some constant times exponential of minus x. So it looks like Gaussian. In fact, it is given that it is Gaussian. We have to find mean and variance. So what's the formula for mean, mu and variance sigma? That is 1 divided by square root of 2 pi sigma square e to the power minus x minus mu square divided by 2 sigma square. Okay. So we want to write this in form of this. So we are given p of x is equal to 1 by 2 pi e to the power minus, I'll take minus outside. So x square plus 2x minus 4 divided by 2. Right. So what we want to do is complete the square. It is x minus mu square. Right. So square root 2 pi e to the power minus. Now we have x plus x square plus 2x plus 4. And this is 4. No, this is x square minus 2x because I took out minus outside. And then plus 4. So this is x square minus 2x plus 4. So how do we complete the squares? You can say this is x square minus 2x plus 1 plus 3. Right. So this is x minus 1 whole square plus 3. So if I write it like this, minus x minus 1 whole square plus 3 divided by 2. So I 1 by root 2 pi e to the power minus x minus 1 square divided by 2. And then there is a coefficient e to the power minus 3 by 2. So if you compare this, by the way, this is 2 times 1 square, right? So if you ignore this one, then on left hand side, you have an exact Gaussian distribution. And this is your mu, this is your sigma, right? Because it matches here. So you have 2 pi into 1 square. Okay. But there is a coefficient here. So that's a mistake of question because it's no longer a distribution, right? Because the total integral won't be 1. But bearing this constant, mu is 1 and sigma is 1. So mu is equal to 1 and variance, which is sigma square, is 1 square, which is 1. Okay. So the answer is this, but with a coefficient that is this. So the original Gaussian would look something like this, but our p of x is a multiplied version of it. So it would look something like this. Okay.
This Gaussian with this e raised to minus 3 by 2 will not it will not be a decaying this thing of the Gaussian means it is shown or it is a constant. Okay, okay,
Yeah,
it
it's
is a
constant.
yeah, yeah, yeah.
Right? Yeah. So it's a Gaussian function, but it's not a Gaussian distribution. Okay. The second question is computing the upper triangular matrix in LU decomposition. We saw this, right, using Python. So this we'll do later when we go to Python code. Third is solving this set of linear equation using Gauss elimination. And this is not using Python, right? But we have studied the Gauss elimination. So let's write the matrix. So first is x plus y plus 3. So x is 1, y is 1, z is 0, and this is x, y, z. This is equal to 3. Second equation is 3x plus 2y plus 1z is equal to 10. Third is 0x plus 1y plus 3z is equal to 11. Okay. So shorthand notation, because we are not going to touch x, y, z, is this 110, 321, 013, then one line 3, 10, 11. Okay. Now we want to make this upper triangle. So make this 0. How do we make this 0? We said that R2 is R2 minus 3 times R1. Okay. So multiply this R1 by 3 and subtract it. So the first row stays same, third row stays the same, second row is 3 minus 3 times 1. So it becomes 0, which is not a surprise. This is why we did this, right? Then this becomes 2 minus 3 times 1. So 2 minus 3, which is minus 1. This is 1 minus 3 times 0, which is 1. And you have to do the same thing here. So 10 minus 3 times first 3, that is 1, this is 11. And this is already 0, so we just want to make this one 0. How can we do that? We can say R3 is R3 plus R2. Okay, so add both of them. So 1, 1, 0, 0 minus 1, 1, and sum of R2 and R3. So 0, 0, 4 is equal to 3, 1, and 1 plus 11. So 12. Okay. So now we have the equation. So first equation is the last equation actually is 4z is equal to 12. This is the third one. This is the second one. This is the first one. So third gives 4z is equal to 12. So z is equal to 3, which means from 2 we have minus y plus z is equal to 1, and z is itself is 3, which means y will be 1 minus 1 plus z, right? Sorry, z minus 1, which is 2. So minus 2 plus 3 is 1. And then 1 is saying x plus y is equal to 3, and y is 2, which means x is equal to 1. So there you go. That's our answer. Okay, 1, 2, 3. You can easily check this. Directly substitute xyz here or use Python. We have done this last time, right? So very easy, and but it needs to be precise, right? So we should have some practice. Okay. Fourth one is again coding question. So you are given an array of x's, then generate y's using this function. Plus there is a noise, so a random number with uniform distribution, and then we have to fit the curve. So this will do later. And last one is also a Python question. So solve this. So find this integral using Monte Carlo. So generating random numbers, a number of random variables is given, and then find the integral. Okay. So any questions in these two that we did? It's clear, right? Pretty easy. So let's jump to coding section. Yeah. So the first one is just a second. Yeah, matrix is given. We have to find LU decomposition of the matrix and then find the upper triangular matrix. So let's first write. Let me just run numpy and pyplot because we are always going to use that. So first is defining the matrix, and AI already gives me the answer right, from this text, I guess. So we write row wise. So 3, 2, 4. That array is the first row, and the second row is 202. Third is 423. Okay. Then we want to find LU decomposition. How do we do that? We do that using linalg. So linalg dot LU of span. That will give us all the three matrices P, L, and U. So we can write P, comma L, comma U equal to this. But we haven't defined linalg. We should import it. So from scipy, import linalg. And then print U. Right? That's the matrix that we want. That gives 4, 2, 3, 0, minus 1.5, 0, 0, 2. It is an upper triangle matrix, right? Because the diagonals are non-zero, but everything below it is 0. In fact, we can print P and S also. P, print S. So P is this permutation matrix. So every row and every column is exactly 1, 1, and L is lower triangle. So diagonal entries are 1, and everything above that is 0. Okay. This third one, for x is equal to this. Now this is slightly ambiguous. I don't really know what exactly they mean, but I'm going to treat it as an array from 0 to 1 with 100 points. Okay. So which is just clean space. 0 to 1 with 100 points. So, let me make this n just to make it generalizable. N is 100. And then see this one. Yeah. So we are generating y. Y is going to be 0.2x. Yeah, this thing 0.2x plus 0.3 times x square minus 1 and plus 0.5 times a uniformly random number, right? So I can write this RND as well, just to go with what is taught in the course, right? So this will generate n random numbers uniformly distributed between 0 and 1. Okay. And it's given that we should set numpy.random.seed to be 0. Now, what does seed mean? Basically, when we generate these random numbers, they are never randoms. Do you know? They are always pseudo randoms. So you have some seed, and then some very complex algorithm to keep on generating new random numbers based on this seed. Right. So why do we use seed? So that when you run this code, you generate the exactly same set of random numbers that I am generating. Okay. So we'll get the same answer. And then what do we want to do? We want to fit the polynomial. So we can write P is equal to polyfit. Yeah, use numpy dot polyfit. So np dot polyfit and x comma y comma 2, and then we write poly is equal to 2. Okay, so it has in fact 5 outputs, but we just want the coefficient. So the others are left blank, right? And then we can print p. So p will be the coefficients of x square, 10x, and then constant, right? It's a degree 2 polynomial. That's what we are asked to fit. And what do we want to find? The constant term, I think. Yeah, what will be the constant term approximated to 2 decimal places? So the constant term would be the third term, so p2, and we have to round it to 2 decimal points. So let's run this, and the constant term turns out to be minus 0.68. Okay, we can in fact plot the data just to see. So let's plot. It's not asked, but it's just for completeness. Fun. So the fit data is y fit is equal to. We can evaluate the polynomial using np dot polyval. Okay, so we have to give the coefficients which are p evaluated at this array of x, and then plot the values. And in fact, I don't want it to be scattered, so I'll erase this. D dot plot x comma y fit. Yeah, this one I'll make scattered. Let's add label also. This is the data. And this is the fit. PLT dot legend. Okay, so this was our data. The original polynomial was just quadratic, right? So and upwards. So it was something like this. But then we added lots of random numbers, which was 0.5 times some number between 0 to 1 with uniform distribution. So on average, this number would be 0.5, right? So on average, we are adding 0.5 times 0.5, which is 0.25. So this coefficient should be close to minus 1 plus 0.25, which is minus 0.75. And this one is pretty close to that, not exact. But yeah, because of this random points, and we don't have so many random points, maybe that's why it's slightly further from minus 0.75, but nonetheless within the range, right? And as we can see that this nicely fits the polynomial. So this is an example of regression.
Can you explain this polyfit, whatever p comma you did no, for the polynomial that pool
Yeah.
equal to?
So let me run this on a new cell. Let me just say np.polyfill. Okay. So it gives tuple of 5 things. First is the coefficients which we needed. So the array containing that. Second is I think the residual. So total error, the least square that we did. And I don't really know what the other 3 things are. Maybe we can check online. np.polyfill. So it returns this p, which is the polynomial coefficient, and the residuals, the error, and v is some covariance matrix. I'll have to see what that is. But the point is that it returns 5 things, but we only want the first thing. Okay. So we say that the first thing, whatever it turns out, call it T. Second things, I don't really need it, so I don't even bother naming it. I can name it. I can call it A, comma B, comma C.
Now,
But
whatever the first thing that we got that array,
yeah,
in that first is the x square term, second one is x term, and third one is constant. Is it
right.
right?
Yeah,
That's
that's
why
right.
we are getting the 0.68 thing, or
Yeah. That is exactly. So our polynomial is 0.44. The fit polynomial is 0.44x square minus 0.07 x and minus 0.67.
yeah, okay,
Okay.
yeah. And pool equal to true does what?
What?
And that pool equal to true here written. No? But x, y, 2 and
I
pool
I,
equal.
I think it. Let me just check. I don't want to say anything wrong. Yeah, so it's which determines the nature of return value. So if we make it false, then it just the coefficients are written. So in fact, the false would have been written. So if we make this false,
Then we'll get only three
only
values. Then
the
do you have to change the left side in that case? On that.
no, yeah, then we just need t is equal to this thing. So in fact, let me make it that way. Why complicate it? Okay. So let's run this. All right. So we get this. So we can do one thing. We can make this 0 just to play around with it. So there is no noise. And then we can see it exactly fits the polynomial, right? So 0.3 is the coefficient of x square, 0.2 is the coefficient of x, and minus 1 is the constant. But as we increase this magnitude of error or the noise that is present, the accuracy of the coefficients decreases. And by the way, no matter how much I run it, I get the same coefficients. Why? Because I'm generating the same set of random numbers because I have given it some seed. If I don't give some seed, then it will generate different answers every time. So now it's minus 0.7, minus 0.78, etc. Okay, so let me uncomment this.
Is there any guideline to choose seed for a particular kind of application, or anything we can choose?
In general, you don't need to choose it. In fact, you should not if there is no particular reason. Now, what could be the reason for choosing the seed is that you want to replicate the result. Okay, because as you can see, I got minus 0.78, minus 0.7, etc. Why? Because there was high noise and less number of data points. So, but the question needs to have just one answer, right? So everyone should get the same answer. So when we want to generate the same sequence of random numbers again and again, then we use the seed. It does not matter what seed you choose. But if you fix the
But
seed,
then why that option is given? Means okay. The thing is, my doubt was like,
mhm,
if we choose n properly and some starting seed properly,
mhm,
then whether we means is there any combination which will actually take us to the true value of the answer?
no,
Nothing
this,
like that.
yeah.
Okay.
So you can look it up. What seeding does basically, it generates a sequence of pseudo numbers, pseudo random numbers, which means if your starting number is same, then all that sequence will be same because computers can't generate truly random numbers, right? There is no randomness in computers. It's in physical system, it's already there in quantum or maybe in chaotic system. But computer, what it does is generates first number that is very random, either using this seed or using current time or something like that, and then generates a sequence based on that seed. So it
Can
looks
seed
random
be
to us.
more than n?
Yeah,
Can seed be more than n?
can seed?
Anything? Can
I
seed
think
be?
seed can be anything.
Yeah.
Just check.
Okay.
Yeah. So okay, it does not give so much information, but you can look it up. Seeding
Yeah,
in
I'll
computer.
do.
Okay,
Yeah.
and the keyword is pseudo random numbers. Okay. By the way, I wanted to do one exercise, which is this one. So this is the data point. So y is this 22. So while I type out, can anyone suggest what these numbers what could mean? What are these numbers? It's a very difficult question. 10, 7, 6, 8, and the x is np dot arrange. Yeah. So these are 30 numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah. Yeah. Let me just in space starting from 1 to 11 using 11 points. And then plot x comma y. I get something like this. Anyone wants to guess what this is? Okay, no, it's very difficult. On x-axis is the week number of this course. On y-axis, can you say what it is?
Attendance.
Yes, yeah, it's the attendance. And I do this every year, and I see this kind of exponentially decreasing trend. Okay, but I don't do it in the classes because it's generally classical mechanics or quantum mechanics course. But since this is Python, I thought we can do this. So it looks like an exponential. So to see that, what should we do? We should take logarithm on y-axis, right? So we can define another array, ln y, which is np dot log y, and then plot that. Okay, so that one is just linear. Yeah, I wanted to comment that one out. Yeah, this is more linear than previous one, and then we can fit a linear polynomial. So x comma y comma 1, which just means straight line, and then print p. So this is the slope, which is minus 1. So the rate of exponential decay rate is about this one. In fact, we can plot this as well using this one. Y effect is equal to this. P dot dot X comma yeah, this label. What did I do? I wanted to plot fit element. Yeah. So this is the rate minus 0.08 per week. And I don't remember, but what I've seen is that this is some kind of universal coefficient that that shows the rate of decrease of human interest in anything. I don't know how universal it is, but this is something interesting. Alright. Anyways, let's do this last question, which is finding this integral using Monte Carlo method. So how do we do that? By the way, I think I forgot to cover that. What did I? Yeah, using this. So this probability means it should be inside this box, right? So you generate a pair of random numbers x and y, and this is your f of x. The probability is that probability that f of x is greater than y, or probability that y is less than f of x. Okay. So we are given this function tan h square of x square from 0 to 1 using Monte Carlo, and n is given to be 106. No, it should be 10 to the power 6. Sorry about that. Yeah. So first we write n is equal to 10 to the power 6. So that is 106, and then we want to generate x and y. So x is np dot random dot uniform, or let's stick with what is taught in the class, which is random dot rnd, because we want it from 0 to n. So open. Wait, this might not work. Let's just see. Yeah, because this is treated as a float object, and this is the number of random numbers that we want. So we should write 10 to the power 6. Okay. Similarly, we generate random y values. Yeah. Okay. So x and y are not same arrays, right? Because we are not specifying seed or anything. So it's generating different sequence. Okay. And then let's define the function itself. F of x, which is, so see the algorithm, this AI does mistakes sometimes. It gives NP of 10h x square, but in fact it is square of this. Okay. And then we want to count how many are inside it. So we start count from 0, and then for, let's do it simple way. I will range n. Yeah. If f of x of I, if it is greater than y, that was the condition, right? F of x is greater than y, then it is inside the integral. So increase the count. Otherwise, don't increase the count. And then this is the probability that count is, sorry, the point that you generated is within the area. So, and to get the area, you should multiply it with the area of the box, which is just 1 times 1, right? Why? Because the length of the box that we are considering can also be taken as 1, because tan h of x never crosses 1. So that's the idea. And it gives the answer as 0.14677, which is the integral. In fact, we can check this online. Integral. Yeah. So this is, if you don't know this, this is where you can integrate stuff and do many other things. So yeah, put tan h of x square dx from 0 to, just a second. Gives answer 1. Oh, did I make the same mistake that AI did? Yeah. Well, I'm as smart as AI. So it is 10h square. Now let's calculate. You can do this using Mathematica also, which is a software by Wolfram itself. It's not giving any result. Yeah, it's 0.16146719. Let's see how close we got. Yeah, pretty similar, right? So if you think about it philosophically, it's funny. We are using random numbers to calculate something that has a definite answer. But once you realize how it works, it makes sense. Okay, so this is 0.14677. You can do rounding off yourself, I think, by now. So that ends the discussion. And just for fun, I had done this calculating of pi stuff. So how many? So I generated n is equal to 10,000 uniform points, and then calculated how many are inside the circle. By the way, you can do zip thing also. Right? If you want to iterate over two arrays simultaneously, then you write x0 and y0 and zip of x comma y. So first x0 is first element of x, then first element of y, then second element of x, and second element of y, etc. Okay. And pi turns out to be 3.1456. And every time it might give slightly different answer, right? Because we are just estimating it. It's taking a while. It's mainly because we are doing the plotting. So 3.1476. So up to almost 2 decimal points, it gives the correct answer. Okay. And there is this thing that I did. It's called Buffon's leader. Maybe I can show it to you, which is also not very good way of estimating pi, but it's like this. You have lots of parallel lines, okay, and you randomly throw sticks over that region. And if the length of the stick is half the length of the separation between the lines, then you look at how many of them crossed and how many of them did not cross. Then the probability is 1 over pi. So if you put L is equal to T by 2, then you get 1 over pi. So using that, you can calculate pi, which is what I have done this. So this will be in the code that I'll share. So you can take a deeper look at it. But what it does is essentially takes some needles, first 100 needles, throws it on this region which has equispaced lines. So distance between them is 1. And the length of the needle is half. Then looks at how many of them cross. So 33 cross. And then probability is 1 over pi. So pi will be 1 over probability. So total needles divided by how many of them cross. So you get estimate to be 3.03. And then you can increase the number of needles and you can hope to get closer and closer. Right. So it gives something like 3.24. And as you increase the number of needles, you get closer and closer to true one. Okay, so this is also an example of Monte Carlo method. Okay, so that ends the discussion. By the way, the questions, the options that were given in the assignments, some of them were wrong as usual. For example, last one should be 0.15, but it gives 0.85, which makes me
No,
suspect.
in this times it is 0.15 also is there
It,
in this year's
oh,
assignment.
okay. Is
But
it the
other
same
question
question?
is having wrong this thing. One more question is having wrong options.
Okay, if it's wrong, then they'll give you the marks.
I wanted you to just go for the this year's question 10. You did not solve that, but again just that using that eigenvalues and eigenvectors. Some
Okay, uh, this is 2024. You mean week 12 or week 11?
week 12.
Week 12 is
Just if you tell the method of means it is very easy actually if we see theoretically, but uh, once we get that values, whether to multiply with the thing or not, I'm not
yeah.
sure.
So let me read the question. Find the eigenvalues and eigenvectors of the following using I function. Let A be the eigenvector corresponding to maximum eigenvalue. What is the value of A rounded to two maximal places, two decimal places? Yeah, so you find all the eigenvalues, and let's
Hmm.
say the first eigenvalue is the highest one. Then find the corresponding the first eigenvector and print its value, and just make it np dot round A comma 2. So what's your doubt?
For that, suppose that is the first or second value is the highest one.
Yeah,
Then eigenvector will be column vector or row vector, or whether we have to multiply with that, or I'm not. Since you take any other example and you just tell which eigenvalue corresponds to which eigenvector.
yeah, let's do that. We had this one. So let's take this matrix, and this is, and then we say let's first print I go. So I have to say right linear dot I. This will work out. Yeah. So we get three eigenvalues: lambda 1, lambda 2, lambda 3. And this is the first eigenvector. This is the second eigenvector. So v2 corresponding to this lambda 2. This is the third eigenvector. Okay.
So, uh, see, for it will be means if we consider 8 as maximum, like anything, like
Yeah.
here 8 is maximum.
Yeah.
So it corresponds to array
This.
bracket 1.
Yeah.
Okay, there also it corresponds to that one only. Okay, then that vector is to be printed. Okay,
Right.
got it. Yeah,
And if you are not convinced, we can do one thing just to check. Let's make it diagonal. So 3, 1, 0, 0, 4. So what will be the eigenvalues of this?
314.
3, 1, 4, which is what it gives. 3, 1, 4. What is the eigenvector corresponding to 3? That's the 1, 0, 0. Right?
Yeah,
Second is 0, 1. This is 0, 0, 1.
got it. Thanks.
Okay. Yeah. Anyone else? Okay then. So just to reiterate, we have a live interactive session with Professor Mahendra Verma on Sunday, 5 p.m. Please do make use of this. It will be very helpful to you. You can ask him any kind of questions. Okay. And maybe I should not say this, but if you are writing the exam, these kind of sessions often tend to help. Right. Okay. So let's meet on Sunday where Professor Verma will interact with you.
Thank
Any
you.
questions? Sure. Bye.
Sessions is from 3 to 5 or 5 onward?
5 onwards. So final announcement will be done on the portal and you will
Okay.
get the link and everything. Okay.
Okay. Thank
Yeah.
you.
Bye. Bye. Bye.
Yeah. Bye.